Let me finish the Newton method, okay, the rigorous, the symbolic Newton method. Then I'll go for variations, okay, in the Newton method, and then that'll be the content for today, okay. So as the hacker practice that you have done last time, right? So you're solving this. You find that in the beginning, right, of your Newton method, it is making very small improvement, because the problem, if you start from this guess at the place where this function is highly nonlinear, you are making very, very small progress, okay? And there are times that when you search the directions, the first step is too large, okay? This is concave up, right? Nonlinearity. Concave up, right? So your initial guess, right, by using the slope is too conservative, right? You can have other situations where it concave the other way, right? So where your first step is way too aggressive, right? So we're treating the essence of Newton method is I treat the local problem as linear and try to predict where is the linear solution. In the highly nonlinear places, before you close the solution, this is undershoot and overshoot, okay? So, but it is guaranteed if you find the slope, you will be approaching the solution, right? That direction is right. You spend the time, if you look at a optimization problem, it is a direction that will make your objective function to be smaller. Or here, in this one, we're solving for f equal to 0. It will be, since we solve the directions, that direction is the right directions, okay? That will give you closer to your eventual solution. It's just that where it's highly nonlinear concave up, you undershoot, highly concave the other way, you have overshoot, okay? And so this is the line search method, okay? Line search method. I know the direction is good. So should I do a more aggressive or less aggressive corrections in that direction? Is the spirit of line search, okay? In here, I will hope, since this direction is correct, in the beginning, I'm only taking 0.01, right? 0.01 of improvement. You need about 99 steps before you go into the quadratic convergence step, right? Because beginning, you're taking very small steps, okay? Is it possible, okay, we introduce a t, okay, since I know presently it's the right direction, I choose a t so that I check around t using a bisection search. Say t can be all the way from 8 to 1 over 8, okay? I compare these values, right? And I try to decide which one is better, okay? By giving me a smaller residue. Right? So this is so this will make undershoot problems to go faster over relaxation. Or here, right, your first step is too aggressive. Cut it down and make it under relaxation. Okay, so this is the line search method. Okay, so it just in our Newton step, okay, you add in a t, right, and that's all that's different. And the penalty is each time you want to know what is the better t, you have to evaluate f. Okay, you are not evaluating Jacobian. Okay, this is worth it if the evaluation of Jacobian is much more expensive than evaluation of the f. Right? If evaluation of f is anyway expensive, then this is the penalty. Okay. Okay. So this is without re-evaluating the Jacobian. I do a line search, but each line search, in order to know whether this is a good choice, you have to evaluate that residual factors norm. And that is a penalty, okay? But line search many times, especially for your non-exact Jacobian, okay? This is an important thing, okay? And this price is usually paid, okay? So that you have a more stable and not too conservative search, okay? I have tell you that this kind of functions happens a lot in nature, okay? This is not a strange function, okay? Something that even in first order chemistry, you will encounter these kind of functions where the reaction energy is on the order of 2 eV and my thermal energy is 25 millivolts. And that happened, okay? Then this kind of function will happen, okay? So if you look at this, right? So line search in the multi-dimensional things, if this is your objective function and this is the minimal or the zero you're looking for, right? This is the called the basin of attraction. Once you fall into this, or you are in the proximity when it's close to zero, okay? Then you will have the quadratic convergence that we have introduced last time. It's not only that you get much faster convergence, but also an indication that your Newton method is done consistently. Okay, so it's an external thing you can check. What is the convergence? Okay, when you approach the solutions, how good is that solution? You can see from the quadratic convergence. Okay, and you can also see there are these kind of, if you have two basin of attraction, then unfortunately there will be a deflection point, right? Where you try to look for the minimum, but between two minimum there's required to be a local maximum. And that local maximum is guaranteed to overshoot you to nowhere, right? Right, because the slope is flat, slope is now, or the Jacobian is degenerate, or the slope is zero. When you are at the deflection point, then you will be, line search will be so critical, right? Because you are at the point where the slope will give you, shoot very, very far, okay? So something that at this point, need to be careful checking that, okay? So if you still have that equation, okay, let's try it, okay? Try the T, so you should be adding about a few lines to add the line search method, okay? So let's see if you can improve the line search method, okay? The same one, okay? This is a undershoot problem. So if you over-relax, okay, over-relax your T, that means T is larger than 1, you should be getting the solution much faster, okay? Instead of waiting for the initial steps of taking the only 0.01 corrections. So let's implement that, okay? Choose the T, maybe let's do it in more ratios for this practice purpose. Search 10, 1, and 0.1, okay? Minus 0.1. Compare these three, whether this 10, 1, or minus 0.1 give you the best improvement in residual factor, and choose that T, okay? See if you can converge much faster. The previous things? Okay. Sorry. It's just that everything is the same. When you use the Newton method to find out the delta x times the T, 10, 1, or 0.1. Okay, so to make that correction. Yes, yeah. And compare which T gives you the minimum and use that T to correct, right? And then go to exactly the next step of update.
So instead of adding delta x, we're adding t times delta x.
Yes, that's the only thing. Line search is single parameter search. Right. And let's make you usually search a T a little bit more carefully, but that's for these hacker things. Let's just compare 3, 10, 1, 0.1. This should eliminate your very slow initial approach and converge within 10 steps, 10, 15 steps. What?
Negative point.
T?
Yeah.
T can no point. Can never be negative. Negative will be. Go ahead. The direction is correct. It's just that you don't know what's the magnitude to take, right? Sorry. Sorry about that stupid error.
Shoots it to 9, not a number.
10 shoot to 9? What do you mean?
T is 10.
10, okay.
So it's giving me 9, 7.
Really?
Yes.
10. 10 for your delta x first calculation is 0.01, right?
The
X.
initial xk is 0.01.
Initial is 1, right?
Okay.
Initial gas is 1.
Yes.
And then your first calculation of delta x should be 0.01,
Oh yeah.
minus 0.01.
Yeah.
Yeah.
Minus, yeah.
So if you times 10 is minus 0.1, so the correction is to 0.9. That shouldn't give you an overshoot, another number though. This is a good thing about using a problem you know the ground truth, right? So you get, in these simple steps, if you originally converge, and if you do line search, give you another number, then your code has problems, right? Because I can hand calculate
Yes.
the first step, right?
Yeah.
Yeah?
So the first step is fine, but like eventually, like the 17th step or something.
17th step is become nan,
Yeah. Negative, yeah.
but you have 1 in there. How can it be bad?
No, t is equal to 10. Oh,
No, you-
initial guess.
No. It's not always take t as 10. Then you are definitely dead. I have no problem with that. Line search means you calculate all the residual of these choices.
Oh.
Which one is better, right?
The most, or
Which is the most improvement?
yeah.
Okay. If you always choose t as a 10, it's guaranteed death, right? Because you will definitely overshoot, right? When you close to linear,
Yeah.
right? So 1 has to be compared, right? Because that's eventually when you are close to the solution, right? And the problem is sufficiently linear. T equal to 1 gives you the correct answer in that quadratic convergence range, right? So you have to compare, okay? Not taking t as a constant. That's guaranteed death, indeed. That's probably where your NAN coming from as well, okay? So it should be around the 8 or 9 step when 1 is actually better than 10, if you implement it correctly.
You take whichever's the most, right? Whichever group is so the highest.
You compare the residual value. I'm solving fx equal to 0.
Right.
Right, so whichever t give you the largest reduction, okay, or closer to 0 residual factor, you take that t. Same thing in optimization problem. You take the t that give you the smallest, right, objective function. Same method. Anyone get the correct search of t? T should be the choice should be 10 in the beginning for about 7-8 steps, and then the choice become 1. Then you get into the quadratic convergence zone. I will wait a while because line search is critical. Okay. Now you have a Newton method that's still pretty good. Okay, when you cannot calculate that correct directions, line search become absolutely critical. Trika, do you get it? Line search? What's the problem? It's longer than I thought.
I'm not like it's doing the line search, but probably I'm doing some mistake.
Where is your function? Let me see.
Function like fx, and then fx, and this is the address. iteration, and here I'm doing the line search. So new
So,
x is
yeah.
x over t times x.
Why t is a function?
T is not a function, T is an array of 10, 1, and 0.1. And
Oh,
it's-
I see. Okay.
Then it is finding out the f, then it is taking the norm of the f and finding the minimum norm, and then that new norm, whichever comes, is the x norm for
X new. The X new line search.
like of all the three x's, which one was giving the minimum.
Okay. And what is the report? Is always 10.
Yes.
What is 10?
But 10 is the t which is chosen here.
Okay. And
It should
it's
go to
it
1.
finished. What do you print out the residual each
Yes.
time? Let's see. Residuals.
This is the f dash.
So delta x is still close to 0.01.
Mhm.
Each time you calculate delta x is 0.1, then at 10 times it's, at the 10th step it's actually converged.
Then
That's an accidental converge. But this, can you calculate, show me your residual factor, right? F. You just show me your fx, right? Not delta fx. Yeah, so it becomes 0. It's accidental 10, when t equal to 10, at the 0.1 step, it gives you the correct answer directly. Okay, so your implementation is correct. Okay. So in one versions, it's actually, because this is such a highly nonlinear functions, and if you have a 0.1 in here, right, 0.1, and you take a step t, that's 10, you accidentally hit the correct solution, and the iteration for sure stop, because you find
I'm getting 0.01.
0.01, yeah, but
So that's delta x, and then that's my, but x is not 0 for some reason.
you're taking the correction in the wrong way. T is the wrong
it's
direction.
increasing.
Yes, yeah.
But delta x is negative.
Yes, so
Don't you
so
So it's x plus delta x.
yeah, if
Okay.
x for sure x plus
Yeah,
delta
yeah,
x,
yeah.
right?
it is becoming, but but it's becoming at iteration 14.
Okay. So
I
it's
did
just
this one
the way you print it.
Yes.
Okay. Okay.
Yeah, but same thing though, but now I'm getting 0.01. Just the way.
Your Newton direction for sure is correct, right?
Yeah.
But this one, right? So you correct it. So if you search for 10, this one should be 0.9, right?
Yeah.
X plus delta x for sure. Okay. X plus t times delta x.
And is delta x just 1 over the...
I know what initially what is the delta x, right? Which delta x should be minus slope,
Yeah.
right? So this for short delta x. Then your x iteration equals to plus. Okay.
Yeah.
So I know this is 100, right? Evaluate it, so you will, this entire thing in the first step is minus 0.01 from this function, right? So your next step, that should be, if you don't do line search, you should search for x equal to 0.99. Right? 0.99, if you substitute here, your delta x is still close to 0.01, right? Because it's a very much undershoot. Right? But if you can make the search, then you will go from original without line search, what you expect is this is x, okay, initial guess, 0.99, 0.98, 0.97. Okay, if you with t, okay, your x should be 1.9, 0.8, 0.7, and then you go down much faster. Okay. So Duke made this example, okay, or things like this example to be part of your test program for your line search. You can do the overshoot problem by using a 1 minus lnx, right? So you define this. This will undershoot like crazy. Right? Is also the answer is at e. Okay, you can use that as a things. But log x will give you overshoot like crazy. Okay, because it's a concave down function. Okay, so you should the t should be small in the beginning before away from the solution. Okay. Okay, to finish this, okay, after I will not wait any further, okay, but do finish the observing the correct behavior of a line search, okay, and I'm going to introduce to you variations of the Newton method, okay. So line search is a good summary word, right? Newton method, evaluation of the Jacobian give you that line, that slope. What direction is correct to give you to the solution, okay? In 1D, this is kind of silly, but in multi-dimension, that direction is absolutely important, right? Because it's a trade-off between all the different variables, which one should increase, which one should decrease, right? To approach your solution, right?
Conversions in 10 steps.
Okay, sure, okay. Sure, okay, and use that as a test case, okay, so line search. So the following method, okay, if you remember this, okay, for many, many problems, okay, that the evaluation of the Jacobian is very expensive. Let me show you that, okay. For all the cases we have done now, right, that the Newton method is operated on a function like this, where you have a symbolic solution for the slope, and you use that to calculate. Okay, there are many situations whether that is impossible. Okay, so we are forced to use something that's Newton-like, but you cannot evaluate the exact Jacobian matrix. Okay. That also, or you mean you cannot evaluate the exact slope. Okay, you can evaluate this function, but you cannot evaluate the derivative. Okay, the problem you have just done, derivative have a closed form. You implement your derivative directly in your computer, and you compute. You're happy. Okay, but many practical problems in multivariate cases, the Jacobian matrix can be huge, even if sparse. Okay, even in sparse, it's huge, okay? Or it's not possible for you to get anything of a symbolic calculation. Okay, your f is it's a function that you collect from the data, and it's a least square fit. The least square fit, the data is everywhere. Okay, you know how to evaluate f, but you cannot write down a derivative of f symbolically. Then you are forced to do something that's not Newton exactly. Okay, exactly. Okay, so these are the Newton-like method. Okay, I'll tell you two most important ones. Okay, two most important Newton-like method for practical problem. Okay, so this is okay. A Newton method is linear variate. That means you do some linear operation to the x and b, you remain the same search. Okay, if it's a linear problem, right? What is Newton method? I guess the problem is linear locally. Okay, so it is affine invariance or linear invariance. Okay, Jacobian can be sparse, but this is something if you can calculate the Jacobian minus 1 required for the search, okay, directly or symbolically, that's great. Okay? If not, then we have to do something else. Okay? So this is a quasi-Newton method. Okay? Quasi-Newton method. I estimate the Jacobian matrix element instead of from closed form, but use a local analysis, numerically get my Jacobian elements. Okay? Now, in comparison with what you just did, okay, if you do things symbolically, there's no round of error, right? A symbolic derivative you evaluate is exact, right? There's no precision issue. But if you evaluate your slope from or a partial derivative from the local analysis, these contain error. These elements contain error. Okay, it's an estimate, it's a local analysis. It's only as good as your delta x, right? If you choose the delta x to be too large, you will be a truncation error. Choose it too small, you will have round of errors, right? We've done that in your local analysis, right? So this is an estimate that contain error, okay? So that means you can use this, formulate your Jacobian exactly the way that you do your search before, but know that it is now even more vulnerable to the wrong initial guess. If I'm far away from that basin of attraction, because my slope or the Jacobian contains errors, the direction you know approaching the solution or the optimizations is have noise, right? Originally, that slope is exact, right? When you calculate this slope is exact. In the multivariate case, everything has a noise because of that estimation. So it has a noise that's making that E can be even vulnerable to instability. Okay, instability. But many times, this is the only thing you can do, right? Because I don't have closed form of your derivative, right? I can only evaluate f, right? I can perturb my independent variable and calculate the slope. I don't have a closed form to evaluate that slope, okay, which is not uncommon. Okay. The second variation is there are problems with a lot of the independent variables. Formulating the Jacobian is too large to even evaluate numerically. It's not possible, okay? So this is the method that I say, let me use the difference of my two solutions, okay, two guess, okay, divided by what is the difference of that in that step, okay? I use that as a slope, okay? So this takes two initial guesses, okay? I need to know the first step and the second step. And I use the first and second step and the two guesses I have to evaluate my slope. Okay? And this direction can be horrible, okay? But this is cheap, totally cheap, okay? In comparison with you formulate the Jacobian is a much larger sparse matrix. Here, I don't formulate any matrix, right? I just say, I am going to evaluate that descent slope from two guesses. Okay, from two guesses, okay? So you can see the scale method is notoriously slow if you are not in the basin of attraction, okay? Even you are in the basin of attraction, it doesn't have quadratic convergence, okay? Because I didn't treat the problem correctly, okay? So that you will can guarantee that if it's linear, it can get my solution to the first step, okay? If I cannot have that, I don't have quadratic convergence, okay? So in here, even if it's cheap, then line search is absolutely necessary. Okay, that's why I want to wait for your line search, okay? So if you define your slope this way, okay, your slope just from, you give two initial guesses, okay, and use that to evaluate the direction you should search, okay? And that direction can be very bad, okay? I have to stabilize it and have to use line search, okay? Line search, again, is only ask you to evaluate f. not its derivative. Okay, so this is still doable. Okay, so they're called the secant method. Okay. So with that, let's try it. Okay, same function. Okay, let's do your quasi-Newton. Okay, instead of taking your f prime x to be, now originally you do this, right? Implementing the this guy. Now don't assume that this is not doable. Okay, you evaluate your search direction just by quasi-Newton. Okay, that means in your routine, when you calculate the derivative, the slope, use a local analysis to calculate the slope. Okay, use a local analysis to calculate the slope. Okay, substitute that and let's observe. Okay, quasi-Newton is not bad. Okay, still eventually give you quadratic convergence. Not bad. Okay, secant method is bad. Okay, because eventually you will lose the quadratic convergence. But let's try the substitution of quasi-Newton method. Should be easy in your routine. Okay, if you do not have the line search working, just forget about line search now. Okay, just work on the initial Newton iterations, but replace your evaluation of the slope by a numerical slope. Okay.
Not what we know.
What?
Not like what we know the closed form.
Yes, yes. Assume that this closed form is not known. Okay. Assume. So you get a taste of quasi-Newton. Okay.
We do it on the second one with the t.
If the t remain, if the line search works, right, keep the t, right? It's only the evaluations of the slope that's different now, right? Keep the line search. For this simple problem, the quasi-Newton should be almost as good as your Newton method. Okay, slower, but almost as good.
The derivative of x goes to 0 after some time. The
Truncated out?
like it's becoming 0. Yeah.
Okay.
After like 100 iterations.
After 100 iterations, it didn't make any improvement anymore.
Yeah.
Okay, so your delta x has to be larger at later, right? When you detect that step size is making this one to be 0, so you overshoot like crazy then.
No, like it gives out 0 division error because that thing is 0, right? So it gives 0 division.
These two are not different enough
Not very different, yeah.
for a precision limited, right?
But it is converging in like 14.
Okay, it's
And then after that, because the delta x becomes 0.
okay. This big two become too close.
Yeah.
So it's the set of tolerance that make your
Yeah.
you further observation.
It's like
Okay.
infinity.
Okay.
But it did get to this scale part. So like initially it was delta x was let's say something, and then in that very next iteration was 10 to the minus 6 of the previous one, then 10 to the minus 12 of the previous one.
That usually we call that convergence, right? But if you continue to calculate that, then these two will become too close, right?
Yeah,
Limited by your precision, right?
That's really nice.
Sure. Yes. Okay. So you get a taste of quasi-Newton. Okay. This is as I mentioned, in multivariable case, many times this is the only thing you can do. Okay, because symbolic form doesn't exist. Okay, you have to do this. Okay, and this also show you that the importance of choosing that tolerance, right? Because now I introduce a local analysis. That means in your search is also subject to a round of error in the evaluation of your slope. So if you make your tolerance to be unreasonably small, because you have precision problem, you can never achieve that tolerance. A very, very small tolerance. Okay, you get that taste. Okay. Okay. For the time I have, so let me say this as a conclusion of today. Okay. So how to teach students software engineering with the goal that you can be a effective programmer to deal with very complex programs is something that we have discussed within the faculty. What is the best course that can be taught? Okay. And there are 3 versions now at Cornell. Okay, this is one version. Okay, the other version is a 5,000 level class in CS called software engineering. Okay, their point is to teach software engineering. There's really the principle is the same as our principle. Okay, modular programming, how to do external testing, regressional testing, code reuse, how to check the spec. That philosophy is the same. Okay, but the best way to teach large-scale programming is just let the student to work with a company that with a large software. Okay, so the first probably all the lectures are online. You can check it out. I think I walk through is still helpful to know the principle. But you learn the programming just by working with a company software. Okay, with a company mentor. Okay. And that company they have 7 companies working with that class. Okay. So that's one approach. Okay. I don't particularly like that approach because I've been in company. So company software for sure many times are good software. Okay. But the many principles not taught. Okay. In one particular software. Okay. And up to now you probably have failed. Bugs can come from anywhere. It comes from your numerical method. Bugs, or you cannot get your solution or the answer you want from all the possible reasons. Your code error, you're not careful about your memory, your formulation has problem, misunderstanding of the spec. All these are possible reasons. When you're not getting your expected answer, how do you achieve that step? Okay, is something that's need to learn on different problems, okay, instead of a company's software. But I think it's one method. You see a lot of the good examples in company software. Okay, that's one way. Okay, and there's another way is teach in the civil engineering. Okay, they deal with very large scale software as well. Okay, and that's MATLAB and MATLAB to death. Okay. And again, it's not bad. Okay, I'm not trying to be sarcastic here. Okay, it's just something it is another way of looking at, let me use the external library as much as possible, okay, and only making the outside observation. Okay, that is a necessary training as well. Okay, don't get me wrong. Okay, so I took a method. Okay, I introduced the software engineering principles along with the method you are writing. Okay, I don't know if this is better. Okay, but I think this tell you something. Okay, but is this the only way? This is definitely not the only way. Is this the better way to teach software engineering? I don't know. Okay. Okay, hopefully, but so I appreciate your feedback, okay, eventually that when you learn to deal with large-scale programming, where you deal with the debugging process or verification, okay, not debugging, verification process of your program, okay, what is missing, okay? Even within the faculty, we don't have a consensus, okay, so I actually searched even the open courseware in MIT. You know, it teach electrical engineering, civil engineering, mechanical engineering, all have their own version to teach students programming. Okay, so it is not a solved problem. Okay, so in pedagogy, it's something that we are not sure. So what is your part that you think that you're still missing that you cannot scale your programming? Okay, please reflect to me, okay? I hope we can learn better. Especially for these generations, I think a lot of the training is different, okay? Multitasking is something that I was not trained when I was young. But multitasking is trained for this generation, okay? So maybe the learning method will be different, okay? So what is the bottleneck? What is the things that you think that if you get that practice, you are getting better skill, okay? Please do reflect to me, okay? It's something that will make this type of classes to teach students become effective programmer, okay? The course material can be even more effective, okay? So now you have seen most of the approach that I have taken, okay? For sure, there are still problems I haven't finished treating, okay? And there are more principles to be taught, okay? But at this point, you get a flavor, okay? This is how I look at how you can grow the scale of your programming. And with that, the evolution of the software come with your modular design and regression testing, okay? It's that process, I hope, okay, that all these different methods to teach you that, okay? I choose this method to teach you that, okay? So if you have feedbacks, please do tell me, okay? Okay, so that'll be it for today's class.